All right, welcome back everyone to Math 162, Week 6, Lecture 2. Got our whiteboard with a few dates, 6.2 homework due on the 1st, that's today, 6.3 due on the 6th, 6.5 we will finish today. We're going to be cutting it very, very close, but we will finish that material today. I planned it appropriately. And that means that the homework will be due a week from today, which is the 8th. And that also means that our second test, as I warned you, it'd be coming right around the corner from the first test because chapter 6 is shorter. So our second test is going to be on the 8th and the 9th, that Thursday-Friday combo. Remember, we give you 2 days for these tests with the exception of the final. So that's only covering 4 sections of material, 6.1, 6.2, 6.3, and then 6.5. I still need to post that little bit of material for 6.4 that I said I would. I haven't done that yet. Again, you won't see any of that stuff on any test, any homework in here at all. It's just in case you want to take a peek at something that might be more necessary once you hit calculus. There is a formula sheet provided to you in Canvas. It's pretty easy to find. Switch this to student view. Go. Formula sheet, boom. And we've talked about this formula sheet and how you'll have some formulas up here, but not others. And then for a couple of the formulas, I give you almost every detail except the pluses or minuses for the tangent sum formulas. So I don't give you any of the sines or cosine formulas for the sums and differences as promised. I do give you the tangent formula with the exception of the pluses and minuses as promised. These are the double angle formulas I promised to give you. So there's one up here that I'm not giving you. And then your half angle formulas, and you can see I had to do a little visual edit here, but don't worry about that, not a big deal. So that's your formula sheet that you'll want to print or have available digitally when you are ready to take your test. Do not add anything to this. Do not subtract anything from this. I can't imagine that you would. But that will be what you use for your test. Now, while I'm not testing you directly on anything from chapter 5, admittedly, almost everything we did in chapter 5, with the exception of graphing, sines and cosines, etc., is still inherently in chapter 6 material and will still be inherently in chapter 7 material. And that is part of why I make test 2 on so few sections, because you still have to have everything in line, almost everything in line, arguably, from the first test worth of material, because trigonometry, this stuff doesn't go away. It would be like saying, all right, test 1 is on addition, and then test 2 is on multiplication. Well, there's still addition inside of multiplication. When you do 3 times 3, you're just adding 3 3s. So it's still implicitly part of the material. So please don't think that that stuff is ever going to go away. I know you've heard me rant about that 50 million times, so I'll keep this one much shorter. So how's test 2 going to work? It's going to be shorter number of questions. Test 1 was, 25? Test 2 is going to be in the ballpark of 15 to 18 because some of these problems are a little lengthier. You've got your formula sheet. This is a no notes, no books, no calculator test still. Hopefully we don't have any issues like I did with the first test where I thought I had an exact answer and it turned out to be a decimal. If that happens, I will of course adjust everybody's grades. So if anything says to approximate to the tenths or hundredths or wholes, you know that something has gone wrong and I will look into it. But again, those test dates will be the 8th and the 9th. So yes, we have class on the 8th. If the only available time you have is on the 8th during class, then you can take the test during then and then just watch the class's YouTube replay later that I always have up and available within an hour of our class ending. So if out of Thursday and Friday, the only free time you have is from 11 to 1, then you take your test during that time, and then you watch the replay on Sunday or Monday or super early Tuesday, but as long as it's before Tuesday's class so that you can stay on pace. This will be the same as last time that you have to submit your work in Canvas within 15 minutes of completion. So make sure that your name is on your work, make sure your work is numbered. They don't have to be in order 1, 2, 3, 4, but they have to be numbered. You will have the same amount of time as last time, 120 minutes. Once again, no calculator, no books, no notes, with the exception of the formula sheet that is provided in Canvas. And just like last time, there is a review in my math lab. It is immediately under the Chapter 6 homework. So you have 6.1, 6.2, 6.3, 6.5, and then the Chapter 6 review. Just like last time, the review will not be graded. So if you do it or don't do it, it won't affect your numerical grade directly. However, I do believe it will affect your grade. If you don't do the review, you're probably going to do a little worse on the test. That's historically what happens. People that do the review do better on the test because I make my reviews comparable to the test. So I'm trying to give you an awesome resource, and I really do hope that you'll use it. If you choose not to, best of luck. I mean, best of luck either way, of course. I want everybody to do as well as they possibly can. So with that being said, we are going to pick up where we left off in 6.5. Again, really long section, all sorts of types of equations that we're going to be looking at. So we're going to relook at the just basic strategies, and then we'll get into the examples again, and we'll do a mixture of some that are bounded and some that are not bounded.
Okay, so reminder, sine, cosine, cosecant, and secant have periods of 2 pi, whereas tangent and cotangent have a period of pi. That issue will come up. If your solutions have a domain that isn't restricted, you must consider the periodic nature of those functions, which that will definitely come up, and this all goes together. So if you don't have a restricted domain, so if I just say solve, and I don't say solve from 0 to 2 pi, then whenever you do your sines, cosines, cosecants, or secants, your solutions, you have to add this 2 in pi because there are infinitely many answers. Every time you go another 360 degrees, the answer is still true. For tangent and cotangent, it's every time you go another 180 degrees, the answer is still true. So that's what this represents, because we can let n be any number. It can be 0, it can be 1, it can be 2, it can be 3, and then there's our first, second, third, and fourth solutions, whatever. So again, all that's paired together. Some techniques that we'll be using: if there's only one trig term, isolate it, and then you'll have something like sine of 30 degrees is equal to a half, and then you can use your triangles, your quadrilantals, your smart trig class, all that stuff to piece together your solutions of what the angle should be. Sometimes the inside won't just be a theta, it might be a 2 theta or a 3 theta or a 4 theta, or it could be x, it doesn't have to be theta. And then we'll have to go through this n equals 0, 1, 2, 3 process, and this will actually come up in another instance as well, but let's just label it for now. We'll get back to it. Let's see, and that's until you go past one period. So once your answers go past 360 degrees or 180 degrees, depending on which trig function you're using, then you're just going to be repeating yourself, basically. So then you just say, well, oh, add the n pi or 2 n pi, or don't, depending on the scenario. Okay, factor if possible. That can help us. Use double angles and or Pythagorean identities. That can be helpful. Now you might say, well, what about half angles? Admittedly, we won't do any with half angles. You might say, well, what about the sum and differences? Admittedly, we won't be doing any of those, but yes, you are right. All of those things could help you potentially, depending on the type of problem you have, but we're going to keep them, and I'm going to say on the simpler side of things, but that doesn't mean you're going to think they're simple. I'm just saying in the grand scheme of things, we're going to be keeping it simple. Watch out for extraneous solutions, which means you get a solution, but it doesn't actually work. Kind of like if you had a rational equation, which means there's fractions with x's in the bottom, maybe x equals 3 looks like a solution, but when you plug it in, it makes the bottom 0, and you can't divide by 0. That makes it extraneous. It means it looks like it works, but when you actually try and verify, it doesn't. So there will be scenarios where that's going to happen. And dealing with that, it's mainly an issue. I forgot to put my little star here as well. That is mainly an issue for sine and cosine, which are bound between, I can spell, just can't type clearly, -1 and 1. Remember, when you have just a sine of x, the biggest the answer could be is 1, the smallest it could be is -1, and the same is true of cosine. And that's because your graphs looked like this, where that's a 1 and this is a -1 for sine of x, or for this for cosine of x, where we start at 1 and go down and come back up, and then all of that value is 2 pi, that value is 2 pi. That's 1, that's a -1. That's what I mean, they're bound between. The heights are bound from 1 to -1 inclusive. I said that backwards. I should say they're bound from -1 to 1 inclusive, but it wasn't the end of the world. So we're going to see all of these little technique issues pop up, whether we're adding the 2 in pi or not doing it, whether we have to go through some of the cases or not. All of these will be seen. Your homework problems should flow similarly. Your test problems should flow similarly. So let's get to it. Remember, if you don't have the chance to write all this down, YouTube is wonderful. It's got a pause feature. So I'll kind of pull this back a little for now, but I won't be able to keep those instructions up too long. Example 1, solve. Big wordy instruction, solve. And I'm not doing A, B, C, D stuff here, so 3 sine x, excuse me, minus 2 is equal to 5 sine x minus 1. So you have seen trig equations before, but they were always very simple. It was like sine of x equals a half, or sine of x equals square root of 3/2, or tangent of x equals 1. This, you got to do some rearrangement to get to that point. But once we get to that point, we have gone through things like this back in that chapter 5 test. It's just a matter of putting everything in one big mixing bowl and stirring it up. So I only see one type of trig term. If there's only one trig term, just isolate it. So pretend like it's just a big, giant, fat X. Move all of them to one side, move everything else that doesn't have it to the other side. Does it matter which side the signs go to? No. Me personally, I try and keep them positive, but it's arbitrary. So I'm going to subtract 3 sine x on both sides. And with those going to the right, that means that the constants need to go left. So I'll add 1 to both sides. If you need to do that in 2 steps, be my guest. That's up to you. So those cancel and these cancel. I don't like keeping that cross out there, so just follow along. And the left side is now -2 plus 1 is going to be -1 equals 5 minus 3 is 2, so that's 2 sine x's. And the sine x is almost isolated, but we need to get rid of that 2. We do so by dividing, because what we're looking at currently is a times. And that's going to give us -1/2 is equal to sine of x. And I'm not done. I'm not saying this is the answer. I'm just pointing out this is what I mean. You have seen a problem like this previously back in chapter 5. You saw problems like this in class, homework, and on the test, where you're trying to find out what angles make this statement true. And remember, quite often, there are more than one answer to this, because sine, you can have for any angle, in quadrant 2, 3, or 4, you can take a reference angle and recreate it, and then it's just the same answer. So let's say if you ignore the plus or minus of this, if this was true for 30 degrees or 60 degrees, and spoilers, it's one of them, but I'm not saying yet, then that means you could take that 30 or 60 degrees and potentially put it in all 4 quadrants as a reference angle and potentially have 4 answers. But because of this plus or minus, sine is only negative in 2 of the quadrants, which means you'd have 2 answers, not 4, not 1, 2. All right, so sine of x equals -1/2. I'm actually going to draw up the little triangle. I know I don't do that too often. I usually pull up the other document, but let's draw it up this time. So here's your reference triangle. This will be x prime, because if that's negative, this needs to be a reference triangle. And then its opposite would be the 1, and the hypotenuse would be 2. Well, that makes this the 1, 2 square root of 3 triangle. And based on memorization of that triangle, your angle being opposite of 1 means that angle is 30 degrees, but we prefer our answers with this stuff in radians. 30 degrees is pi over 6. So that says x prime is pi over 6. Again, yes, it is 30 degrees, but we're going to stick to radians for this stuff. So that's the reference angle, but clearly the reference angle won't work because all things are positive in quadrant 1. So we need to find out where is sine negative. So we say, but sine of x is negative in quadrants. Let's see, a smart trig class. Sine is the y value. When you go down, y is negative. Down is quadrants 3 and 4. So our reference angle of pi over 6, we need to put in quadrants 3 and 4. So that's going to be 2 solutions. Let's find the first one in quadrant 3. So let's put our pi over 6 here. So there's pi over 6. There's our reference angle in quadrant 3. And that angle is just there. But we need to find the actual angle, which would be starting from the positive x-axis. Now, if you're thinking in degrees, this is 30 degrees, it would be 180 plus 30 degrees, but it's in radians. 180 is pi, so that says our first solution, which I'll call x1, x sub 1, would be pi plus pi over 6, which is 6 pi over 6 plus pi over 6, just getting an LCD, which is 7 pi over 6. So that is our first solution. That is the first solution. Now let's hold on to that. What's the second solution? The second solution, we need to put that reference angle in quadrant 4 instead. So now, this is our reference angle right here of pi over 6, but we need to find the actual angle here, starting from the positive x-axis and going counterclockwise until we hit that. Now, let's think of this in radians, 30 degrees. You'd need to do 360 minus 30 to get an angle that's in quadrant 4. So we're not doing degrees there, we're doing radians. 360 is 2 pi. So that says x2 is 2 pi minus pi over 6. Again, you might need to think about this in degrees and then do your work in radians. You could also do the actual math in degrees and then convert to radians. I don't care how you get the job done. And then 2 pi, when you get an LCD of 6, will become 12 pi over 6 minus 1 pi over 6, but we don't write the 1. 12 minus 1 is 11. So that's 11 pi over 6. That's our second solution. So with those things combined, I'm just going to say x is equal to, and I'm going to do this wrong for a second. 7 pi over 6, I'm going to leave some space, comma, and then 11 pi over 6, and I'm going to leave some space. Let me write that a little smaller. Leaving some space for a reason, but if I just do this, guess what? It's wrong. Let me put the whole problem up here. I said solve. I did not give any restrictions. Sorry, my nose is stuffed up. With no restrictions, you've only given me 2 answers. And this is, what is that? 210 degrees and 330 degrees. But there's no restrictions. X can be any value. So if I add another 360 degrees, there's another answer. If I add another 360 degrees, there's another answer. If I add another 360 degrees, there's another answer. I could subtract them a million times, and there's another answer. And then I can do the same thing to the 11 pi over 6. So with this problem, because this had no restrictions, because I didn't say it was from 0 to 2 pi, something like that. That's what a restriction looks like. I did not do that, which means we have to do that thing I said earlier. The domain is not restricted, and since we were dealing with a sine, we add 2n pi to the solution. That is us just adding 360 degrees over and over and over and over and over, or subtracting 360 degrees over and over and over. So we got to go plus 2n pi to both of these. That is every single solution, infinitely many solutions, in fact, two core solutions of, again, in degrees, 210 and 330. But then you can just add or subtract as many multiples of 360 degrees as you like, and then that is still true because of coterminal angles. And it's very frustrating when you're doing this as homework, and even more on a test probably, when you get this aspect and this aspect right, but then you forget to consider the domain and the whole thing's wrong. Now, again, this is another case of if you submitted your work and you emailed me and said, Mr. Beckner, I got this one wrong. Can you take a look at it? I think I had a lot of details right. I think I just forgot the 2 in pi. I can go, oh yeah, I looked at your work and you're right. Here's 4 out of 5 points, something like that maybe. Or 3 out of 5 if you made another mistake somewhere. You get the idea. But I can help you out if you show your work and point it out to me. All right. So that was example 1. No restrictions, because I did not write somewhere I would have said on something like 0 to 2 pi. That is a restriction. We will see that, but not quite yet. Example 2. Let's do tangent of x minus square root of 3 equals 0. I stopped writing. I did not write on 0 to pi or 0 to 2 pi or anything like that, so there are no restrictions, which means there should be infinitely many answers. So we're going to have to add one of those things to our cores. All right, well, I only see one single type of trig term, so it's probably in our best interest to isolate it. That's what those instructions previously said. I'll scroll back up. If there's only one trig term, isolate it. This will be a lot easier to do. You're just going to add square root of 3 to both sides. Not even going to show that work. If you add square root of 3 to both sides, I lied, I will. Since it's a radical, I'll show the work. That gives us tan x equals square root of 3. Give me a second. Okay. So again, what you can do is think about your reference triangles. Oh, square root of 3, if it's not a 0 or a 1, it's probably one of the triangles. If it's a 0 or a 1, it's probably usually a quadrantal. Tangent's the exception because when tangent's 1, that's 1 over 1, which is 45 degrees. Okay, so tangent's opposite over adjacent, but I don't see the adjacent. So remember that anytime you have just a top number, you can always write it over 1. So just note that this is the same thing as saying tan x is square root of 3 over 1. So you can see your opposite and adjacent. You can draw your reference triangle. Now I can say x or I can say x prime. Since it's positive, you might say it's just x. And you might be right for this since it's tangent, but if it was sine or cosine, it wouldn't technically be right. It would just be one of them. So let me just call it the reference angle. Opposite of square root of 3, adjacent of 1, well, that's the 1, 2 square root of 3 triangle. So that says that your reference angle is 60 degrees, also known as pi over 3. Again, you have got to be able to go between radians and degrees like that for things like 30, 45, and 60, and 90, and 180, and 360. Now the question is the reference angle one of the solutions? Well, since this is positive, tangent is positive in quadrants 1 and 4. I said that wrong. Tangent is positive in quadrants 1 and 3. I was thinking of cosine for some reason. I don't know why I had cosine in my head, but tangent is positive in quadrants 1 and 3, based on a smart trig class. A, all, quadrant 1, all, so tangent. Smart trig, T, tan, quadrant 3, positive. So here's where things get interesting. tangent's positive in quadrant 1 and 3. So normally we'd have to take this angle, put it in quadrant 3, and then go from there. Take the reference angle, put it in quadrant 3, and then you'd get, what, 4 pi over 3. But here's the thing. We're only going to consider quadrants 1 and 2 for tangent, since its period is 0 to 2 pi. 0 to pi. Why do I keep putting cosine in my head for some reason? It's awful of me. It has a period of pi. So you get to pi by quadrant 2. That's weird. So that's just quadrant 1 and 2. So we're not actually going to worry about putting our reference angle in quadrant 3 because, let's scroll back up a little. We said for tangent and cotangent, you don't add 2 n pi, which was 360, you add n pi, which is 180, so just multiples of 180. So any answer that's in quadrant 1, when you add 180 degrees, you're going to put it in quadrant 3. And then from quadrant 3, when you add 180 degrees, you'll go back to quadrant 1. So you'll keep bouncing back and forth between quadrant 1 and 3. So you would actually be not wrong, but redundant if you put your reference angle in quadrant 3 and said that was the second core solution. I'm making quotes with my fingers there that you can't see. And you would actually label 2 different sets of solutions, and my math, I would mark it wrong. I could go back and say, well, here's 4 out of 5 points because that's technically correct. It's just written in a goofy way. So that's why you need to understand with tangent, you only worry about quadrant 1 and 2. All right, so that says x prime. Oops, back to black. So the first solution is x prime, which is pi over 3. There's no need to put that in quadrant 3, as we've already talked about. When we add the n pi, it'll pick it up. With no restrictions, so the actual solution is pi over 3 plus n pi. Again, that is we're taking 60 degrees and then adding 180 to find the next. 60 plus 180 is 240, and that's exactly what you would get if you put your reference angle of 60 in quadrant 3, because 180 plus 60 is 240. So that 240 is picked up right here when n is 1. When n is 2, you'll end up getting 420. When n is 3, you'll end up getting 600. And then 780, et cetera, et cetera, et cetera. And you can go into the negative angles as well. You can subtract 180, 360, 540, 720. All right. So that was example 2. I'm going to highlight this memo for a second because it's about to be relative. I'm going to write something else regarding that. If the inside of the function is not just an x, you're going to need to go through some cases of your n. And what you might even want to do is a substitution. A lot of people struggle with this if they don't do this substitution technique I'm about to show you, because, well, let's just find out. So when inside is 2x or 3x, etc., a substitution is a great idea. In other words, you're going to say, let theta equal to, and then whatever the inside was. If it was 2x, let theta be 2x. If it was 3x, let theta be 3x. There we go. Then Find all theta values that work, then convert back to x, and only then do the n equals 0, 1, 2, 3 until you're outside 360 degrees. Or the other restrictions. Final memo for this. Make sure, and in all caps, because the order you do this matters, add the npi or 2npi. I'm not saying divide, I'm saying whichever it is. In the theta solution. 5 exclamation marks. This is the thing that people get wrong. By this I mean when you add the 2npi or the npi part. A lot of people will just do it at the very end once they have the x equals. That's where they want to add it. But that's not true. You have to put it where you have theta equals, because the solutions that you find will be based on your substitution, and the substitution solutions will be every 360 degrees or every 180 degrees, whatever. When you go back to your x, that multiplier actually has an effect. Remember when we were graphing sine of x versus sine of 2x versus sine of 4x, the number in front of x made one waveform happen quicker. So if one wave happens in 360 degrees for sine of 2x, that wave happened in 180 degrees. Sine of 4x would happen in 90 degrees. Sine of 8x would happen, you get a full period every 45 degrees. So that multiplier inside of a trig function changes things. But when you're in the substitution, when you're in theta, you're thinking about everything happening in 360 degrees, but when you go back to x, things could happen in less than 360 degrees. And that's why you have to do that addition before the final part. So what I'm going to do is I'm going to do an example 3 with an a and a b. It's going to be literally the same equation. One of them I won't give a restriction, then the next one I will, and we'll compare and contrast. All right, so example 3. This is where it starts getting a little weirder. For A, and all the instructions are solve. Sine of 2x is equal to negative square root of 3 over 2. It's the whole problem. There's no restrictions. The inside is not just an x or a y or a theta or whatever. It's a 2 something, 3 something, 4 something. That is what we were just discussing. So what you need to do is you need to say, to make this easy on yourself, let theta or whatever letter you like equal the inside. This should not be the first time you've ever done a substitution technique. We do that in 2 different types of problems in Pre-Calc 1. So now what this problem is going to become is, and I'll keep it in blue since I'm doing a change of variables, it's now just the sine of theta is equal to negative square root of 3 over 2. Well, we can draw up our little reference triangle, or if we already drew it somewhere else, we could just pull from there. That's a negative, so this is definitely a reference theta. And its opposite would be the square root of 3. The hypotenuse would be the 2. This is the 1, 2 square root of 3 triangle that you should have memorized. Since it's opposite the square root of 3, that makes this the 60-degree angle, which is pi over 3. So the reference angle, which could be a solution, maybe it is, maybe it isn't, is pi over 3. That is not a solution to the original equation. That's a solution in this new variable. We went from dollars to yen. So the answer in yen might be 500, but that's not the answer in dollars. You'd have to convert it. And a yen is about a penny roughly, so it'd be about $5. And again, that's roughly. It's not quite 1 to 100 anymore, but not the point of the problem. So that's our reference angle, but sine is negative here. So sine is negative. Let's see, us smart trig class. So it's positive in quadrant 1 and positive in quadrant 2, which means it's negative in quadrants 3 and 4. So we need to put our reference angles in quadrant 3 and 4. So if we draw up a reference angle in quadrant 3, it would look something like that. Here is our pi over 3, and then our actual angle would be going from 0 to there, which would be pi plus pi over 3. So the first solution would be the pi over 3 plus pi. The order you write them doesn't matter. I usually write the pi first. Got to get an LCD. Told you it's never going away. That's 3 pi over 3 plus pi over 3, which is 4 pi over 3. Then let's put a reference angle in quadrant 4. So here's our pi over 3, meaning the actual angle swings till here, which is that 360 minus the angle case. 360 is 2 pi. So our second solution would be 2 pi minus pi over 3, which is 6 pi over 3 minus pi over 3, which is 5 pi over 3. Now, some people will stop here. They say, oh, 4 pi over 3 and 5 pi over 3, and that's wrong. First of all, there are no restrictions, so you're forgetting to add the 2 in pi. All right, so the next student, the student remembers, oh, okay, I got to remember to add the in pi. Remember, I even had this all capitalized. Make sure you add the in pi or 2 in pi in the theta solution. So that's where these need to go. So now what we can say is, putting all of that together, so our theta solutions are 4 pi over 3 plus sine has a period of 2 pi, so adding 2 in pi, or it can be the 5 pi over 3 plus the 2 in pi. And then somebody boxes this up and ships it out, and they get it wrong because you're still in yen, and I asked you a question in dollars. Oops, drop something. So we're not done yet. Let's go back to our little instructions. So you find all the theta that work. We've done that. We found all infinitely many angles that would solve this thing in terms of yen, but we want it in terms of dollars. So now we have to convert back to X. And then this only blah, blah, blah part, this may not even be an issue. Like I said, it's based on restrictions, and we didn't have restrictions, so maybe it's a non-issue. So let's convert back to X. We said that theta was 2x. So now instead of writing thetas, let's write 2x instead. So now we go back to X. So I'll use a different color. So instead of writing theta equals blah, 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 we write 2x equals blah, blah, blah. 4 pi over 3 plus 2 in pi. And then the other one would be 5 pi, oops, blah, 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 blah. I forgot the theta equals. 4. And the theta part would be 2x equals 5 pi over 3 plus 2 in pi. Here's the first one, theta equals this part. That was this, not just the 2 in pi. And then this one is this equation. These used to say theta equals, now they say 2x equals because theta is literally 2x. We made that decision. Now all we do is solve for x, which is literally nothing to do. You just divide each thing by 2. Divide each thing by 2. But notice something. If you didn't put this plus 2 in pi originally, if you waited to the last second, you would just write a plus 2 in pi once you have your x equals. That is not what you're going to see for the actual answer, though. So when you do these divisions, you get x for the first one. 4 pi divided by 3 divided by 2 ends up being 4 pi over 6, which reduces to 2 pi over 3. I'm going to show that arithmetic in a minute. So 2 pi over 3. Again, that's what this becomes. I'll show the arithmetic in a hot second. But these 2's will just directly cancel to get you a plus in pi. And then, or it would be x equals, those 2's canceled. This 5 pi over 3 divided by 2, this turns out it's 5 pi over 6. And then these 2's will cancel with the in pi. These are our solutions. So infinitely many solutions, but it doesn't have a period of 2 pi. This says that it has a period of pi. So these solutions are occurring every 180 degrees, every multiple of 180 degrees. So these are periodic in pi, not 2 pi. And the reason for that is because this 2 here makes the period happen quicker. It happens twice as fast. If that had been 3, it would have happened 3 times as fast. So then your period would end up being 2 pi over 3. All right, so where did this math come from? All right, the 4 pi, let's just squeeze it over here. 4 pi over 3 divided by, that's divided by 2 over 1, 2 over 1. So that's 4 pi over 3 times 1 over 2, and then the 4 reduces to a 1, and the 2 reduces to a 1, giving you, the 4 reduces to a 2, excuse me, your 2 pi over 3. For the 5 pi over 3 divided by the 2, that's divided by 2 over 1, so that's 5 pi over 3 times a half, which clearly gives you your 5 pi over 6. Now, I did not go through n equals 0, n equals 1 equals 2, any of that stuff, because this problem did not have any restrictions. So again, this whole little let the n equals 0, 1, 2, 3 is only if you have restrictions. Notice I said or other restrictions. So that's why I did not do anything having to do with n equals 0, 1, 2, or 3 here, because this problem had no restrictions. Now what I said is I'm going to take this exact same problem and I'm going to give it a restriction, the same restriction we've already seen at least once. I'm going to say it's bounded from 0 to 2 pi. All right, so for B, we're going to solve sine of 2x. Equals, what was it, negative? I think so, yeah, negative square root of 3 over 2. But now it's going to be on 0 to 2 pi. There are several different ways that we can label the restrictions. This is using interval notation, which is my favorite way, but they could just say under 1 full revolution, which would imply the exact same thing. Now, you might say, oh, okay, well, do I need to do the whole let theta equal this, reference triangle, get the pi over 3, but that's a reference angle, put in quadrant 3 and 4. No, this is literally the same problem as A. It's just this is the only thing that's changed. So if I were to do this on a test, what you could do is you can just say, by example 1A, or by problem 14 on the test, we know the solutions in general are x equals 2 pi over 3 plus n pi, not 2n pi. Again, if you had put the 2n pi in there for the x part and not the theta part, that would have been your mistake. You would still have this part and this part right, but you wouldn't have divided the 2 out, so you would have missed it over here and here. And that is a massive mistake because you'd only have half of the solutions. So we know in general x equals 2 pi over 3 plus n pi and 5 pi over 6 plus n pi. So we're just going to take that, but with the restrictions. So 2 pi over 3 is an answer, then 5 pi over 6 is an answer. And then there'll be another answer if we add 180 degrees, and there'll be another answer if we add 180 degrees to this one. And then maybe there's another one if we add another 180, and another one we add another 180. So we just need to actually go through n equals 0, 1, and 2 until we get answers that are bigger than 2 pi. So with the restrictions, we just let n equals 0, 1, 2, 3, da 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 da, until we're past 2 pi. So if we let n equals 0, the first case is letting n be 0. So we're just going to both of these things. We're just making this n a 0 and this n a 0. Well, adding 0 does nothing, so you just get 2 pi over 3 and 5 pi over 6. There's two solutions. Now let's try plugging in n equals 1. N. Plug in to n 1. So now those n's over here are just becoming ones. We're just running through all possible cases. That's all we're doing. So x equals 2 pi over 3 plus 1 pi and 5 pi over 6 plus 1 pi. Let's get LCDs. So that's 2 pi over 3 plus 3 pi over 3, then comma, 5 pi over 6 plus 6 pi over 6. 2 plus 3 is 5, so that's 5 pi over 3 for the one in front of the comma. 5 plus 6 is 11, so that's 11 pi over 6 for the one after the comma. So that's 2 more solutions for a total of 4 thus far. Now, you've got to start asking yourself, are these too big? Are either of these solutions bigger than 2 pi? Or even if they are 2 pi, that's too big because that's an open-ended restriction. So 2 pi is not included. But 5 pi over 3, 5 divided by 3 is 1 2/3, so that's fine. 11 divided by 6 is 1 5/6, so that's fine. It's just if you divided those and you got a number bigger than 2, or if you even got 2 exactly, it's too big. So let's try n equals 2. Now, I can actually tell we're going to get past solutions that work, because if I add another 180 degrees, because every time we add another pi, we're adding another 180 degrees. So adding pi for n equals 1 made us 180 degrees past it. So if we started at, say, 2 pi over 3 is what, 120? Adding 180 to that is 300. If you add another 180 to 300, that's too big. It might not be so clear in radians, so someone may do this legwork. Same thing for this. If you add another 180 degrees to this, you're definitely past 360. So 2 pi over 3 plus 2 pi now. Again, that 1 for the n is now a 2. Or it could be 5 pi over 6 plus 2 pi. I'm going to skip showing the LCD work. You're just going to end up getting, what's that, 6? So that's 8 pi over 3. That's 12 and comma 17 pi over 3. 8 divided by 3 is bigger than 2. 17 divided by 6, not 3, excuse me. 17 pi over 6. These are both too big. So that means we only get 4 solutions. We get x equals 2 pi over 3, 5 pi over 6, 5 pi over 3, and 11 pi over 6. That's a long problem because in doing this problem, we didn't even do half of the work because I borrowed it from a previous example. Imagine if I hadn't done it that way. We'd still be working on the problem. So when the inside is not just an x or a theta or a y or just a single letter, if there's a multiplier there, it complicates things more than anything else in this entire section, in my opinion. Because you have this substitution to run through, you have to make sure that you add your periodic nature at the appropriate point. So in the substitution part, not the final part, because the final part has to take that 2 into account, and it causes it, again, to speed up. Things happen twice as fast or 3 times as fast. So this additive periodic nature value changes. It gets smaller. We're good? Okay. So that's the first major complication. The second major complication is if I give you one where you have the number inside and I give you restrictions, holy cow, that's a pain in the butt. That's a long problem, but it's a perfectly valid problem, and it's something that you have to understand to be able to reason through. So you've got to do your if this was a completely new problem, I'd do my substitution. I'd find my solutions in theta. Then I would add the 2 in pi because it's sine. Then I'd go back to x. Then, because of the restrictions, I have to go through n equals 0, 1, 2, 3, et cetera, et cetera, et cetera. There's a lot of details here to keep up with. Now, am I going to throw 5 of those on a test? Absolutely not. It would be 1 of them at most, and that is definitely a 1 at most. So let's do something different. For example 4. Let's take something that looks like this. 2 sine of x plus 1 times 2 cosine of x minus the square root of 3. Then equals 0. And we're going to solve this on 0 to 2 pi. So I am giving you restrictions. I'm telling you the number one mistake students make is they don't pay attention to restrictions. I'll give them restrictions and then they'll add the 2 in pi at the end, or I won't give them restrictions and they forget to add the 2 in pi at the end. But that one little detail will make it go from right to wrong in the snap of a finger. And again, on a test, you show your work, you point it out, you could get partial credit, but homework, it just means you're gonna have to do it again, and that's a headache. Especially if you miss it 3 times in a row, and then you gotta start over. So, one of the instructions, let's go back to the instructions for just a minute, said to factor if possible. We have gone through the, if there's only one trig term isolated, we've gone through the, we might have to do a substitution and a n equals 0, 1, 2, 3 stuff. We've done all that. The next one is factor if possible, because there might be like a sine squared somewhere, or there might be just a GCF potentially. That's what I'm starting to get into. And when you have a factored equation, you set each factor equal to 0. Well, I gave this to you pre-factored, so that's nice. But because it's factored, we follow that 0 product rule. Which says we can just set each factor equal to 0 on its own. So we can set the 2 sine of x plus 1 equal to 0. That'll be its own thing. And then let me give myself just enough space. And then we set the other thing, which is 2 cosine of x minus the square root of 3 equal to 0. That's old algebra. So this is two equations that we have to solve. Pay attention to reference angles, a smart trig class, remembering restrictions. So we're not going to be adding a 2n pi here. Now, even if there are no restrictions with those substitutions, we still had to do it. I mean, even if there are restrictions, we still had to do it. Let me point that out. So back on this example, there are restrictions here. So you might think, oh, I don't have to add that 2n pi bit. But yes, you do. Whenever you have a multiplier inside, even if it's restricted, you have to add the 2n pi or n pi, whichever is relative. And you have to remember to add it for the theta section, not the final x section. It's a lot to keep intact in an order. All right, so let's just subtract 1 on both sides. You'll get 2 sine of x equals -1. Divide both sides by 2. You get sine of x equals -1/2. Let's go ahead and clean up this other one. Add square root of 3 to both sides. You get 2 cosine of x equals square root of 3. Divide both sides by 2, and you get that the cosine of x has to be square root of 3 over 2. See, these don't end up being just random numbers. We end up seeing a lot of these same familiar numbers. Square root of 3 over 2, 1/2. Square root of 2 over 2, or 1 over square root of 2 maybe that you could clean up. 1, 0, -1. Those are the types of numbers we should anticipate to see, because I'm not going to give you something that you need a calculator for and to get a decimal approximation to. I'm giving you something that you can use your quadrantals, your 30, 60, 90, and your 45, 45, 90 triangles. I could be mean and make it so you need double angle formulas, half angle formulas, maybe a 15 degrees is involved. I'm not doing that. That would be torture in trig class, a regular trig class. All right, so where is sine of x equal to -1/2? Why does this seem so familiar? Why does this one right here just sound so familiar? I feel like if I scratch my brain hard enough, it sounds weird, doesn't it? But I like it. If I scratch hard enough, maybe just let me see. What do we do? Sine of no, no, no. Oh, this is why it seems familiar. Sine of x equals -1/2. We have already found the solutions to that. So this is another case of, if on a test, if I gave you one problem that was simpler and you got this, and another problem you've got more going on and you notice something that you've already done before, don't reinvent the wheel. You can just say, by example 1, so by example 1, we know x is equal to, now those solutions were, shoot. Sorry about that. I should have put them in my brain. I scratched too hard. 7 pi over 6 and 11 pi over 6 plus their 2n pi's. Now, this example was not restricted, so it had the plus 2n pi's. This one is restricted, so we don't need to add the 2n pi's. There's no extra little 2 or 3 inside, so we don't have to go through the cases. So it's just 7 pi over 6 and 11 pi over 6. Again, I do not need to add the plus 2n pi's because we are restricting this time. And there was no 2 or 3 or 4 inside with that x. Those are the things that make us need to add the plus 2n pi. Big time-saving element. Feel free to use that on a test whenever you can. So there we go. That one's done. This one, however, we have not seen. We're going to have to do the legwork. So, all right, cosine of x equals square root of 3 over 2. Let's draw our reference triangle. And again, we're considering all 4 quadrants. So even if this is a solution, I'm going to call it a reference angle for now. Adjacent should be square root of 3. The hypotenuse should be 2. That makes the opposite 1 because it's the 1, 2 square root of 3 triangle we've memorized. You can do Pythagorean to figure it out, but you should memorize that one. So that says x prime, since it's opposite the 1, that's the 30 degrees, which is pi over 6. Now, cosine, this is positive, Cosine is positive in quadrants 1 and 4 based on a smart trig class. A all for quadrant 1, C in quadrant 4 for cosine. So cosine is positive in quadrant 1 and 4. So that means our first solution over here, it's technically the third solution, but I'm just going to write a little 1 here, is pi over 6. And the second solution we got to put in quadrant 4. So let's draw our angle in quadrant 4. So here's our pi over 6. But our actual angle will go all the way around this way, which would be 2 pi minus pi over 6. So x2, 2 pi minus pi over 6, which is 12 pi over 12 minus pi over 6, which is 11 pi over 6. So the solutions from this one are pi over 6 and 11 pi over 6. But our solutions are all of them, not just the sines problem, not just the cosines problem, it's all of these. But look really carefully. What do you notice? That's right, that you answered to yourself, I hope. 11 pi over 6, 11 pi over 6. We saw the same solution twice. Do we really need to write the same solution twice? No, we don't. So since we have an overlap, we're only going to write it once. So we just say for the solution x equals, and I'll put them as in, I'll even put them in ascending order. You don't have to, but I'm going to, is pi over 6, 7 pi over 6, and 11 pi over 6. That is the solution. There's no plus 2 in pi's or any of that because there were no, because there were restrictions, and there were no 2x's or 3x's inside of the trig functions. So the 11 pi over 6 just happened twice. It was seen twice. There's no need to write it twice. All right, I think we have time for one more and we'll call it a day. But let's just re-look at this because the next problem eventually we'll get to this, what it started as, not the same thing, but just the type of parentheses, zero product rule, and you'll have two different equations to work through. Do you see why I tried to emphasize so heavily back in chapter 5 that if you don't learn chapter 5, you can't do anything in this course? Because this right here was a problem in chapter 5 that people already struggled with. And now that's not even like 1/4 of the problem itself. It's like chapter 5 is us learning how to add, subtract, multiply, and divide. And then chapter 6 and on is us trying to solve equations with that stuff and simplify fractions and decimals with that stuff. Again, I'm not saying that's the process. I'm just giving you a similar relationship. I think I can fit example 5 here. Solve 2 cosine squared x, that's a first today, plus cosine x minus 1 equals 0, and we're going to do this on 0 to 2 pi. The restrictions do not have to be 0 to 2 pi, but it is a common restriction because then we're just saying one full circle. That's the most common type of restriction. And it's the way most of us tend to think, but again, in the grand scheme of things, without the restriction, we're supposed to think of the infinitely many answers that are possible. It's kind of like saying, all right, if you have $50,000 worth of bills, how much money do you need to make? And someone says $50,000. No, that's not true. That's one answer. You can make $51,000, $59,000, $59,273.14 after Uncle Sam takes his taxes and whatever. There are infinitely many answers to that problem. You don't have to make exactly 50,000. The answer would be 50,000 or more. All right. So back to the instructions. Scrolling, we're scrolling, we're scrolling. Factor if possible. Now you might say, well, what about Pythagorean? Use Pythagorean. Would that be helpful? Question mark? Because I saw cosine squared. Maybe we want to make that 1 minus sine squared. So someone will see this cosine squared and say, should we make that 1 minus sine squared? If this was a sine, I would say, yes, do that. If this term was also a sine, I would say to do that so that then you would have everything in terms of just one trig function. However, we're already in terms of one trig function, so Pythagorean might not actually help us. Instead, what we want to do to start this is factor. So if you need to show a substitution, this is like thinking about, this is a similar problem, 2x squared plus cosine of x minus 1 equals 0. This is basically what we're factoring. It's just, I'm calling this x and this x. Or you can make them y's, so they're different letters, and you're doing an actual substitution, however you need to do it, but this is just ordinary factoring. You can AC method it, you can trial and error it, and I wrote cosine there, didn't I? Because I have cosine stuck in my brain. That should have been just a x. There we go. Now it's right. Sorry for that. So with a 2x squared, the only possibility the first terms can be are 2x and x. With that being a 1, the only possibility is those to be 1s. Trial and error is ridiculously short here. And then in order for the outer and inner to come to a positive 1, the larger product needs to be positive, which is the outer product, which makes a 2x. So that'll be the plus. This has to be the minus. Again, factoring is on you. If you're rusty with factoring, go do 100 or 1,000 of them. So what I'm going to do is I'm going to just say, instead of writing x's, I'm writing cosines. So the factored form is 2 cosine of x minus 1 times cosine of x plus 1 equals 0. Some of you may not even do this blue stuff over here and go straight to that. That's perfectly fine. Some of you need to see this in a simpler looking form and would do the blue version. That is also fine. Do I care which way you do it? Nope. I care that you can get it done with a way that works always. All right, zero product rule this bad boy, or bad girl, whichever. So we get 2 cosine of x minus 1 equals 0. Or we get cosine of x plus 1 equals 0. Give me 15 seconds. All right, basic algebra. Add 1 to both sides, you'll get 2 cosine of x equals 1. Divide by 2, you'll get cosine of x equals a half. Make my equals a little nicer, and my s. For the other one, you just got to subtract 1 on both sides, and you get cosine of x equals negative 1. All right, one of these equations at a time. So let's just focus on cosine of x equals a half. Well, let's draw up a reference triangle, or use whatever one you've already drawn, the two that you've already got drawn, however you're doing this. Here's our reference angle. Adjacent is 1, hypotenuse is 2. Well, that's the 1, 2, square root of 3 triangle once again. I love that triangle. I love it more than the 45, 45, 90, because at least the cosine and sine are different. For 45, sine and cosine are the same, so you can kind of cheat the system, maybe. So that says x prime has to be, since it's opposite the square root of 3, that's 60 degrees, also known as pi over 3. Now cosine, this is a positive half. Cosine's positive in quadrant 1 and 4 based on a smart trig class. So that says the prime angle, the reference angle, is the first one. But the second one we'll have to put in quadrant 4. So we put our reference angle in quadrant 4. Here's our pi over 3, but our actual angle would swing all the way around, which ends up being 2 pi minus pi over 3. So x2 2 pi minus pi over 3, which is LCD of 3, so that's 6 pi over 3 minus pi over 3, which is 5 pi over 3. Now there were restrictions on this. We were from 0 to 2 pi, so I don't have to add the 2n pi to these solutions. We got pi over 3, and we got 5 pi over 3. So far, we have pi over 3 and 5 pi over 3 as our answers. Those are the only two solutions to the cosine x equals a half from 0 to 360. But we're not done. We have the second equation, cosine of x equals negative 1. And you might say, we'll make that a 1 over 1, and then you try to draw a triangle where the adjacent's 1 and the hypotenuse is 1, and that triangle literally doesn't exist. So you have to remember, wait a minute. When you have a sine or cosine equal to 0, 1, or -1, that's a quadrantal. So you go back to, all right, well, where is cosine negative? Well, cosine goes like x, the x coordinate on the unit circle, and -1 is right here. That's our -1 comma 0. The x coordinate's -1. In terms of an angle, that's 180 degrees. So x has to be equal to pi, 180 degrees. There is not a second solution to that. And that's pretty common for the quadrantals unless it's a 0. If this was cosine x equals 0, then we would have answers of pi over 2 and 3 pi over 2, since this is 0 comma 1, positive 1 there, and then this point is 0 comma -1. So if this was cosine x equals 0, you would get two solutions of pi over 2 and 3 pi over 2. But the 1 or -1, those only happen once for the quadrantals. So here is our third solution. So we got x equals, for all of them together, pi over 3, that was our first one. I'm going to put these in order. Pi occurs next. They don't have to be in order unless it says, and I don't think it tells you to do it that way. And then 5 pi over 3. Again, if there were no restrictions, I would be adding 2 n pi to each of these. There were no restrictions, so we're done. So that is all the time we have today. We have a few minutes left, but like I said, there's no way we can finish example 6 with only 5 minutes remaining. So when we come back next time, we'll have examples 6, 7, 8, and 9. So we got 4 left. One of them's a little weird, admittedly, but we'll figure out why it's weird. Another one is weird in the thing I said not to do to this problem. We said, oh, I saw a cosine squared, so maybe I want to write that as 1 minus sine squared. But I said, don't do that because these are already the same trig term. If they're different terms, then you would want to do that. Spoilers for example 8.
All right, just setting up for the last part where we are going to cover those 4 examples, unlike what I said for quote next time. It's just what I'd say when I'm closing out a video recording session. Sometimes it doesn't work out so well with the phrasing. I think I just covered up what I said on accident. I think my mic was off. I'm just setting up for the next video right now. Obviously, we are going to be finishing those 4 examples. It's just sometimes when I end my videos, that's what I say out of habit, and it obviously is not the case here. So just give me 20 seconds.
Point 5, trig equations. We gave you some reminders about the periods of these because this comes up in almost every problem. We went over some basic techniques, some of which have some similarities to techniques when we were dealing with verifying identities. We said to watch out for extraneous solutions, which we have not had this happen yet. Spoilers for today, since it's the last section, or the last couple problems of the section. We said that identities might need to be used. We've talked about how you have to consider the domain restrictions, whether you're going to add that 2 n pi or whether you don't. We've talked about when you have to go through n equals 0, 1, 2, 3, all those different subtle details. All right. So if you need any refreshers on that, I suggest that you pull up last classes or the last 2 classes notes. We finished off at example 5. So now we're at example 6, and we're going to solve tan x parentheses cotangent of x plus 1, excuse me, equals 0. That's an ugly misplaced 0. There we go. And we're going to solve this on 0 to 2 pi. So this, again, is a restriction. When you have restrictions, you usually don't have to add the 2 in pi. You usually don't have to go through the n equals 0, 1, 2 stuff. It just depends on if there's any, like if there was a 2 here or a 3 here, then you would have to go through some of those. All right, well, this problem, at least in the first step, is easy because everything's factored. It's already factored. You've got one factor here and you've got one factor here, and it's already set equal to 0, which is perfect. So we can just go ahead and apply the 0 product rule. So we can do the, was I switching colors? No, I was not. ZPR means 0 product rule. So the tangent of x is equal to 0. Or we can say the cotangent of x plus 1 is equal to 0. We're separating this into cases. Now, tangent of x equals 0. You're trying to find all angles that when you take the tangent of that angle, it spits out 0. Well, clearly, since this is a 0, it can't be using either of the two triangles, the 45, 45, 90, or the 30, 60, 90, because none of those sides were 0. The only way this is possible is for the quadrantals. That's the only way the tangent can be 0. It's either 0, 90, 180, 270, or 360. So we got to figure out which one it is. So remember that tangent is the ratio of y over x. So remember, tangent is the ratio of y over x for the coordinates. And then when you have your unit circle, boom, 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 boom. So y over x, that means the y has to be 0. It can be 0 over whatever. So the y value is 0 when you don't move up or down, which would be this point and this point, which are 1, 0 and -1, 0. In terms of degrees, that's 0 degrees and 180 degrees. Or, in terms of radians, like I prefer, 0 and pi. Again, tangent is the ratio of y over x. 0 over 1 is 0, 0 over -1 is 0. So those are the 2 points on the unit circle that would correspond to solving this. Well, in terms of angles, that's 0 radians and pi radians, or 0 degrees and 180 degrees. Now both of those are inside 0 to 2 pi, so they're good, and we don't need to add any plus 2 in pi, because plus pi, because this is tangent, you would add plus in pi, but if you take 0 and add pi, you get this solution. If you take pi and add 0, I'm sorry, if you take pi plus pi, that's what I was doing wrong in my head, you get 2 pi, which is already past where you want to be because of that parentheses. All right, cotangent plus 1 equals 0. Let's subtract 1 on both sides. So we get cotangent of x equals -1. So we're looking for the ratio. Again, tangent's y over x, so cotangent would be x over y. To be a -1, well, that can't happen on the quadrantals because one of those is always a 0 and one of them is a 1. So this is going to be one of the little right triangles. So cotangent needs to be -1. So that says that tangent is opposite over adjacent, so cotangent is adjacent over opposite. That has to be -1 over 1. Well, let's not focus on the negative for now. If you got your little triangle, that just says the adjacent needs to be a 1, the opposite needs to be a 1. Well, that's the 1, 1 square root of 2 triangle, which makes this pi over 4 for our reference angle. But it's a negative, so this is just a reference angle. We need to put that in the appropriate quadrant. So then we have to come back and say, well, cotangent is negative in quadrants what? Well, it's in the same quadrants that tangent's negative. Well, they're all positive in quadrant 1, and then us smart trig class T says tangent's positive in quadrant 3. So if tangent's positive in quadrant 1 and 3, that means it's negative in quadrant 2 and 4. So we need to put this reference angle in quadrant 2 and 4. So to put this in quadrant 2, it would be like this. This would be our pi over 4. but then our actual angle would be that, which would be pi minus pi over 4. Which is 4 pi over 4 minus pi over 4. So we'll call that x3. So that would be 3 pi over 4. Putting the angle in quadrant 4, however, sorry, that looks a little crooked. It's like a politician doing math. So here's the pi over 4 reference angle now, but the true angle is this, and that solution, the fourth solution we're finding, would be 2 pi minus pi over 4. It's 360 minus the reference angle, which 2 times 4 is 8, so that's 8 pi over 4 minus pi over 4, which is 7 pi over 4. And then we just like to put our solutions all in one big section. So 0 and pi, and I'm going to try and put them in order. So 0, pi, well, 3 pi over 4 comes before pi. So 0, 3 pi over 4, pi, and then 7 pi over 4. Or in terms of degrees, 0, what's that, 135, 180, and then 325 degrees for all of them. Those are our 4 solutions. No plus in pi's. If I didn't have this part, then each of those would have had plus in pi, again, for each one of them. Not 2 in pi because we're dealing with tangent. Tangent is periodic under pi, not 2 pi. So that's the one subtle change that can mess you up, can make you go from having everything completely right to everything, I mean, completely wrong as my math lab says, but on a test, again, if you're showing work and you're emailing me and say, Mr. Beckner, check out question number 3, then I go, oh, okay, you just added the in pi. Not a big deal. Here's 4 out of 5 points, something like that. But practice and get it right the first time so we don't have to worry about those details. So this problem, you did not have to factor, it came pre-factored. That doesn't have to be the case. I could have certainly given you this as a problem, tan x, cotan x, and then plus tangent of x equals 0. And what's interesting is some people would then go, oh, well, this right here, tangent times cotangent cancels each other out, so that's just a 1, because those are reciprocals of each other, and you get 1 plus tangent of x equals 0, and then you're just solving tangent of x equals -1, which you're only going to come up with solutions of the 3 pi over 4 and the 7 pi over 4. You would not get the 0 and the pi. So that's one interesting aspect of solving trig equations. When you have something like tangent times cotangent where they would cancel each other out, you could be removing solutions or possible solutions to the original problem. It's kind of like when you have a rational equation and we say, don't just multiply everything by the LCD to clear it because you might then be missing information, or some people might just try and get rid of the denominator. And they'll say, well, you can't do that because you'll be missing information. And that's kind of the same idea. So you have to be careful with something like that. And that's why I actually would not give you the problem written this way, because someone might go and cancel it and only get half the solutions. And it seems like you're right, but you made something go away that, again, while it can go away, you're removing a complexity to the problem. I'm just erasing everything I wrote above example 6 in blue. Very slowly. There we go. All right, example 7. Will I have enough room? Yes, I will. Sine of x minus 2 sine of x times cosine of x equals 0. Now this minus 2 blah, blah, blah could have been on the other side. And then you'd say, well, it's probably a good idea to just move everything. Now, what I was talking about earlier, I think I may have even said it backwards. I think I may have said instead of multiplying, what I meant to say is you shouldn't divide. So you might say, oh, well, there's a sign here and a sign here. Let's just divide everything by sign. to get rid of it, I'm doing something you shouldn't do, because then you're getting rid of a complexity of this. You would only have the -2 cosine, and you will end up removing solutions. That's why we never divide out common factors in equations like that. We factor them instead. So again, what I just did was an awful idea. Never, ever, 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 ever do that. You will remove solutions. It goes again with the tangent and cotangent canceling, which again they do. And yes, technically you can divide everything by sign, but you're removing too many layers of complexity. Factor. Well, what can I factor? I don't see any sine squares. Well, I do see a sign here and a sign here. That makes it a GCF. So here's a GCF, sine x. So we're going to pop that sine x out, open a parentheses. Then we're like dividing them. We're not doing it on both sides. It's still over here. It still exists. So sine x divided by sine x is 1 minus. The 2 will stay. The sines will cancel, and we'll be left with the cosine of x. If you don't trust me, distribute that back, and you'll get the original equation. Now we can zero product rule this. We can set each thing equal to 0. So sine of x equals 0. Or 1 minus 2 cosine of x equals 0. So 2 completely different equations. Whenever you see a 0 for just a regular old trig term, that's probably a quadrantal. Sine goes like y. Remember, sine is the y coordinate on the unit circle. We're trying to find y coordinates that are 0, which are, well, coincidentally, the same as setting tangent equal to 0 here and here, which that's 0 degrees and 0 radians and pi radians, or 0 degrees and 180 degrees. Again, that's 1 comma 0, negative 1 comma 0. You don't have to redraw this every time. You can just reference the unit circle. Now, in terms of showing work, this would be excellent for showing your work, because if I just see you go from here to the next thing and all I see is 0, I'm going to go, well, where is you relaying that information to me? If it was pure memorization, that makes it harder for partial credit. If you show me something like this, I can probably scrap together a point or two. So again, x equals 0 and pi based on those 2 points where they're located on the unit circle. Now for the other one, you can subtract 1 on both sides, and you'll get negative 2 cosine of x equals negative 1. You can then divide both sides by negative 2 to get cosine of x equals positive 1/2. Alternatively, you could have added 2 cosine of x and then divided by positive 2. Don't care how you get your algebra done. All I care is that you can get to here. All right, so cosine of x equals 1/2. So here's a reference triangle. There's our x prime, where the adjacent's 1, hypotenuse is 2. Oh, that's the 1, 2 square root of 3 triangle. And that says that x prime has to be, since it's opposite the square root of 3, pi over 3. It's the larger angle. But we need this cosine to be positive. Cosine's positive in more than just one quadrant. Cosine is positive in quadrants, which ones? A smart trig class. So all in quadrant 1, so that's one of them. The reference angle will be one of them. 2 smart for sine, so no. T trig tan, no. C cosine class. Boom. Quadrant 4. So quadrant 1 and 4. And again, that's because cosine goes like the x, and x is positive on the right side of the graph. So x3 is pi over 3 because that's in quadrant 1. But for the fourth one, we need to put the reference angle of pi over 3 in quadrant 4. So here is our pi over 3, meaning that our actual angle is this. So x4 would be 2 pi minus pi over 3, which is 6 pi over 3 minus pi over 3, and that's 5 pi over 3. So far, 1, 2, 3, 4 solutions. I'm going to write this incorrectly. I'm about to write this incorrectly, and I did not give myself enough space, did I? It's going to mess everything up. Hold on, I'm thinking. Still have two more. Come on, scroll down, please. Why won't you scroll down? Okay, that's good enough, whatever. Trying to make this work. Boom. And I can get rid of all that. Go away, please. There we go. Don't understand this program sometimes. All right. Let's recollect our thoughts now that my insanity is done. We had our 1, 2, 3, 4 basic solutions, all within 0 to 2 pi. So if you do this, if you box this up and shift it up as your answers, it's wrong. And you might go, oh, well, I must have messed up somewhere here. No, you didn't. Oh, I must have messed up somewhere here. No, you didn't. No, we didn't. These were all accurate answers, but they're not all of them. Mr. Beckner, you just said that was all of them from 0 to 2 pi. Yes, I did. I never said that there were any restrictions to this. Nowhere did I write on 0 to 2 pi or on 0 to pi or pi to 2 pi, whatever. There were no restrictions, which is why this is a terrible answer. We have to add, since we're dealing with cosine, 2n pi to every single one of them. And the very first one, I'm going to write it. I'm going to erase it. Actually, let me just make a little memo here. Actually, for the first one, it's 0 plus 2n pi. But 0 plus anything is the anything. So that first solution, I'm not going to write as 0 plus 2n pi. I'm just going to write 2n pi. So every multiple of 360 degrees, 0, 360, 720, 0, 2 pi, 4 pi, 6 pi, 8 pi. That's what that says. Negative 12 pi, negative 14 pi. That was the 0. Now let's take the pi. So that'll be pi plus 2n pi, and that's all you can do there. There's no simplification. Then we have the pi over 3 plus 2n pi. Then we have the 5 pi over 3 plus 2n pi. No, I did not put these in ascending order, and that's because of the periodic nature we're invoking in here. You could have taken this one and put it second if you wanted it more in a true ascending order, but there's nothing wrong with writing the answer this way. It's frustrating if you had those 4 solutions right and then you get it wrong because you forgot your 2n pi's. It's just as frustrating if it goes the other way, if you put the 2n pi's and you weren't supposed to have them. So know when you need them, which is when we give restrictions, and know when you don't. You also need them when you have a problem that had a 2 or a 3 or a 4 or something like that inside of a trig function. We talked about that in a previous class. Go back and watch that again. Look over your notes again if you need reiteration. All right, example 8. We're getting there. We are getting there, believe it or not. Sine square root of x minus 4 cosine of x plus 4 equals 0. Now, I alluded to this type of problem last class. Now, if this was a little different. If this was not a cosine, if this was a sine, I would say just go straight to factoring. If that was sine squared and sine, go ahead and try and factor. But it's not. So what we have right now are 2 different trig functions, which we generally don't like to have unless it's already pre-factored, or if it's just a GCF that we can take out. But there is no GCF here to take out at all. So what you want to do is use one of your Pythagorean identities, which says to swap out a sine squared or a cosine squared. What we have is a sine squared, so we're going to swap it out for its equivalent. Now, if you don't remember its equivalent, you better know that sine squared plus cosine squared is equal to 1. You don't ever forget this. You don't ever get to forget this for the rest of your mathematical careers. If you move the cosine over, sine squared of x is 1 minus cosine squared. I highly suggest knowing that off the cuff, that cosine squared is 1 minus sine squared, and vice versa. Because we see it so much. So that's the replacement I'm going to do here. So that becomes 1 minus cosine squared of x. I don't need any parentheses because nothing else fancy is going on there. Then minus 4 cosine of x plus 4 equals 0. Well, the 1 and the 4 make a 5. The cosine squared should be the first term, so that's negative cosine squared of x minus 4 cosine of x plus 5 equals 0. And then some of us might be able to go straight to factoring. Me, though, and most students, we struggle with factoring when there's a negative for the leading term. It messes a lot of our common techniques up. So you have two options. Option 1, which I will erase in a second, this is the longer algebraic version, is just move everything to the other side. So you add cosine squared, add 4 cosine x, and subtract 5 on both sides, and that would make the leading term positive. And that's what I tend to do in an Algebra 1, Algebra 2 class. But I'm going to give you the shorter version here. Multiply both sides by -1. So we take -1 times the left, -1 times the right. This will get the same job done. Because a negative times a negative, all these signs will just switch. Now our positive term will be leading. Cosine squared x plus 4 cosine of x minus 5 equals 0, not -0. And then we can factor. We said if you need to see the similar version of this, so we can say this is similar to, you could just use x squared plus 4x minus 5 equals 0, which you'd factor like so. Factor pairs of 5 are 1 and 5, not a lot of options. To make sure that they subtract to a positive 4, you go plus 5 and -1. That means that the factored version of this is cosine of x minus 1 times cosine of x plus 5. Some people don't do any of this side work and still get it right. That doesn't matter. It's whatever you need to do to get it right. And now here we apply our zero product rule, which means we set each factor equal to 0. So we set the cosine of x minus 1 equal to 0. And then we set the cosine of x plus 5 equal to 0. First one, add 1 to both sides, you'll get cosine of x equals 1. And this is only possible on a quadrantal. Tangents are the only ones that are 1 on non-quadrantals. Again, quadrantal, 0, 90, 180, 270, 360, etc. So we're trying, remember cosine is like an x-coordinate for the unit circle. So we're looking for x-coordinates that are +1. Well, here's our unit circle. The only time x is +1 is at 1, 0, which is 0 degrees or 0 radians. There's only one solution to that. From 0 to 2 pi. You might say, well, hold on, Mr. Beckner, why isn't it this one? Because that point is -1, 0, and -1 is not +1. All right, how about cosine of x plus 5? Well, subtract 5 on both sides. You get cosine of x equals -5. Now that is obviously not the unit circle. It's only 1s and 0s for the unit circle, or undefined. Okay, well, that's obviously the, all right, well, cosine of x, that's, we can say that's adjacent over hypotenuse. So that means the adjacent is -5/1. So we need to draw a right triangle where the reference angle has an adjacent of 5 and a hypotenuse of 1. And then we go, well, what is this side? And if you did this, it would end up being 1 squared minus 5 squared under a square root. which is the square root of negative 24, which is not possible. What that means is it is not possible for the cosine of x to be equal to negative 5. Now, maybe you didn't think to drop this triangle. There's another way you can determine that too. But because that's not possible, there is no solution to that segment. I'm not saying there's no solution overall, I'm saying it's no solution to this piece. Alternatively, with cosine of x equal to negative 5, I made a statement at the beginning of the section. Watch out for extraneous solutions, mainly an issue with sine and cosine, which are bound between -1 and +1. Because on the unit circle, the largest that x coordinate can be or y coordinate can be is a +1 or -1. It means the answers can be no bigger than that, unless you have an amplitude factor, which we don't. And if we did, we would have divided it out. See, cosine is bound between 1 and -1, but we have it being equal to a -5, which is completely impossible. It is extraneous. There is no solution to that segment. So that's what I mean by alternatively, cosine of x is bound from -1 to 1 in the range. -5 is, quote, too big. And by too big, I mean in absolute. The biggest that thing could have been was a +1 or a -1, and we've gone past that. So no solution. Again, just to that segment. But we still had the 0. So our answer is 0, right? You can say x equals 0, and you box that up and you ship it out, and my math lab tells you it's wrong. Why? Because it's not good enough. Look at the original problem. I don't see on 0 to 2 pi. I don't see any restrictions. This was non-restricted, which means we have to add, since we're dealing with sines and cosines, 2 in pi. So we go, our solutions are 0 plus 2 in pi, but 0 plus anything is just the anything. So in other words, our answer is every 360 degrees, going up or down. 360, 720, -360, -720, 0, 1080, -1080. Keep adding and subtracting 360. Or just in terms of pi, 0, 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, 12 pi, 14 pi. A lot easier to rail through those. Another strength of radians versus degrees. Adding 360 degrees over and over can get kind of tedious. So this is the thing to watch out for with extraneous solutions. When sines or cosines are set equal to numbers that are bigger than 1 in absolute. Notice I said in absolute. So your sines and cosines need to be set to things like a half, square root of 3 over 2, square root of 2 over 2, or negative any of those things. -4/5, -19/20, +11 over a million. But it cannot be equal to 11 or a million or -11 or -a million. Tangents can, cotangents can, secants and cosecants can. Sines and cosines are the only ones that have this very, very tight bounds. What's interesting is secants and cosecants are actually bound to everything outside of -1 to +1. So they can't be between -1 and 1. They're everything else. It seems really weird, but that's because of that reciprocal nature of them. All right, last but not least, and we're going to kind of tie some things together that we did last class just to reiterate them. Too far. Example 9, will I have enough room? Yes. 2 sine cosine equals 1. Now be careful here. Some people will go, what I'm about to do is wrong, I'm going to pull out red for wrong for a second. Oh, well, zero product rule, the left side's factored. So we go 2 sine x equals 1, and 2 cosine x? No, it actually wouldn't be the 2. It would just be cosine of x, because the 2 is already accounted for here, equals 1. But it's called the 0 product rule for a reason. They have to be set equal to 0. It's not called the 1 product rule. It's not called the 17 product rule. This is completely and utterly garbage, trash. It's wrong, 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 wrong. You can't do it. This is not the 0 product rule. You would need to move the 1 to the other side. You would have to move that 1 over there by subtracting, and then try and find a way to factor this, which I don't see. If you see it, then you're a better trigonometrician than I am. So, I'm stuck because I can't factor this, even by moving the 1. I can't 0 product this. If I move the 1, it's not a product, and this 2 is just really screwing us up, as well as the 1 with everything on the other side. These are really messing us up this time. Now, we've had the 2 in front and it not be a problem before, but how it's messing us up here will also be a strength. So let's go back to the very beginning, those instructions. And something we haven't done yet, we have used Pythagorean identities, but we have not used any double angle identities. Now, I said in the real world or a class past this, you may need half angle identities, you may need sum and difference identities. Those are all possible. But in this course, homework tests, it's just the double angle identities that might come up. So cosine squared minus sine squared is cosine of 2x, or 2 sine x cosine x is sine of 2x. I almost said that wrong. I had to think. 2 sine cosine is sine of 2x. So again, as a reminder, and scrolling is going to take forever. There we go. So as a reminder, 2 sine of x times cosine of x is the double angle formula for sine. And I'm about to put the 2 in the wrong spot. Sine 2x. So that entire left side we can just change to the sine of 2x. Is equal to 1. Now this right here is a problem. We should not be solving any trig equations directly with that 2 there. It will throw us off, because this is that whole, I'm giving you a problem in dollars, you're going to have to convert it to yen, and then go back to dollars in the end. So this is where we had said, and I'm not going to scroll back up and down again, because we've already done an example like this, that because of that, we need to do one of those substitutions. We say, let theta, or whatever letter you like, y, I don't care, equal to the inside, which is 2x. So this just becomes the sine of theta equal to 1, which we do know how to solve. Now again, after you've done hundreds of these, you may say, well, I know how to solve it with the 2 there. I can account for that later, and that's up to you. That's your own prerogative. I will even say that when I'm railing through trigonometric equations for whatever reason I kind of do that too. But I will also say that I make more simple mistakes when I don't show my substitution work. So sine of theta equals 1. It's only possible for sine to equal 1 on a quadrantal on its most extreme cases. So we're trying to find on the unit circle where is its y value 1, because sine goes like y on the unit circle. Well, that would be here. That point is 0, 1. Now you might think it's here, but that point is 0, -1, and the negative is not positive, obviously. So that says theta is equal to whatever angle that is, which is pi over 2. And you might box it up and ship it out, and it's wrong. It's very wrong. That is our solution in what I'm calling yen, or pesos, or euros, or pounds, or whatever currency you like that's not dollars. If I ask you a question in dollars, you need to answer me in dollars. I don't want to say, well, how much does that calculator cost? And then you tell me 10,000 yen. Well, I don't understand yen. Give me the answer in dollars, please. Thank you. But here's another issue. With this being a 2, I'm going back to the highlight, with this being a 2, the period of sine of 2x is not 2 pi. It's going to happen quicker because that too is a factor that affects the wave speed, as we've discussed. We've said that the period is 2n pi over b, which the 2 here is the b. So what we have to do, even though, so I said this was, I did not say this was bounded, so we know that we do a plus 2n pi somewhere. But if you keep going, if you kept going and said, oh, okay, well, this is 2x equals pi over 2, so x is equal to pi over 4, and then you go x equals pi over 4 plus 2n pi. This is what a lot of people will think the answer is, and this is wrong. Because we added the 2n pi to x and not theta, we accounted for the period too late because some other things have happened. This thing was moving faster, and this being a 2n pi does not account for it happening faster. The period is not 2n pi anymore. It's going to be smaller than that. So again, it was critical that we don't add that too late. You add it for the theta. It was also critical that even if this was bounded, we would have to do this anyways, and then just go through the n equals blah, 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 blah cases. So this is our theta, but we said theta is really 2x. So let's go back to the standard American dollar. Theta is 2x, so that's 2x equals pi over 2 plus 2n pi. And then you can just divide each side by half or multiply, I'm sorry, I said that wrong. You can divide each side by 2, or you can multiply everything by a half. That works too, because I know some people, when they divide by 2, that middle one's going to throw them off, even though I've done that many times in class. So let me just show you the alternative approach. Instead of dividing by 2, you multiply everything by half. I'm going to put the 1/2 here because it's kind of squished. So that says x is equal to, these 2's cancel, these 2 cancel, but these 2 stack up to make a 4 in the bottom. So x equals pi over 4 plus n pi, not plus 2n pi. So you still get the primary angle correct, but you would have the period addition wrong. You would actually end up missing half of the solutions, because this says there's another solution every 180 degrees. If you had plus 2n pi, you would think that the solution happens every 360 degrees. So when you add that 2n pi in a substitution problem is critical. Now, I said this was our last example. You could call it, I'm about to do part 2 of it. You could call it example 10. I'm going to call it example 10 just for fun, but you're going to see some similarities. We've done this before already. Same exact equation, but a bounded solution. So that means you would not have the plus n pi there. And you might think, oh, okay, well, then just the answer is pi over 4. Just cut out the periodic nature. Unfortunately, it does not work that way. Whenever you have these problems where there is a number that ends up inside of a trig function, this is worst case scenario in my opinion, because you have to add the 2n pi at the right time, and you have to remember that you can't just cut that out for the boundedness. You actually have to go through the n equals 0, 1, 2, etc. cases. Until you get to a solution that's too big. So x1, which is n equals 0. Some people might call that x sub 0 to match, and that's okay. It doesn't matter the order of them. That's just going to be pi over 4 plus 0, which is pi over 4. Second solution, which would be n equals 1, would be pi over 4 plus 1 pi, which is pi over 4 plus 4 pi over 4, which is 5 pi over 4. And that's not too big. If it was 9 pi over 4, that would be too big. If it was 8 pi over 4, that would actually be too big because it's exactly 2 pi, and that's a parentheses. If there was an x3, you'd be doing pi over 4 plus 2 pi, Now, this right here is a giant clue that the answer is too big. If you add 2 pi to anything, you're already outside of 2 pi. Not even going to show the algebra because of that. So your only solutions would be pi over 4 and 5 pi over 4. I'm going to tell you, but not write. I would suggest that maybe you write it. I'm going to tell you a pretty strong hint. So the n equals 0, n equals 1. How do I know how far to go? Well, I said you go until the answer is too big. I can do you one better. Whatever number is inside with your x is how many n's you need to go through. So we did n equals 0 and 1 because that was a 2. If that was a 4, I would have 4 unique paths of n. N equals 0, 1, 2, and 3. 4 would be where it would get too big. If that was sine of 12x, I would need to go from n equals 0 to 11. That 12th one would be too big. So that's actually a pretty nice hint as to where to stop. But remember, you only go through the n values if it's bounded. You generally only add the n pi or 2n pi if it's an unbounded problem, with the exception of problems with numbers inside the trig function. So once again, this number right here, let's say that was a 17, and the solutions were bounded, so you had to go through n equals 0, n equals 1 equals 2. I can tell you that the 17th one is where it would be too big. It always works that way. Now, do you have to know that fact? No, because once you get an answer that's too big, you can tell it's bigger than 2 pi. But you may make a mistake and maybe you're missing one, or maybe you went one too far and you're not paying attention to the size. So again, that's the number that the n starts to become too big. It's just a nice little clue. It's not mandatory, but it is helpful. I went too far back. There we go. So that right there will close out chapter 6.
And just in the nick of time, but just pulling up the whiteboard for the last minute we have. Number 6.2 is due today, 6.3 is on the 6th, 6.5 we just finished 5 seconds ago, so that'll be due on the 8th. And remember, that means our test 2, our second of our 3 regular tests, obviously excluding the final exam, that'll be on the 8th and 9th, whichever day you are available to take that test. 2 full hours. Make sure you show your work and submit it to me. Email me for any partial credit requests. Make sure that you have that formula sheet from Canvas available to you during the test. Remember, you will only get 1 attempt for this test. Remember that there is a review in my math lab immediately under the 6.5 homework that you can use to study. Besides that, I think we've got everything else in order. Good luck working on the stuff from 6.5 as well as anything you haven't already finished. Good luck with the review. Email me if you have any questions per usual. Have a great weekend, and we will see you on Tuesday ready to pick up chapter 7.